Welcome back. This is Fundamentals of Micro and Nano Fabrication. I am Sushobhan Awasthi from IC Bangalore. And this lecture we shall continue the module on additive processing. Till now we were discussing chemical vapor deposition. We finished details of chemical vapor deposition, but we will spend one lecture on atomic layer deposition, which is essentially a form of chemical vapor deposition, but the details are significantly different. So it's worth understanding and learning about it in a separate lecture, right? So let's get started. So atomic layer deposition, as the name suggests, is layer by layer growth. In this extreme case, that layer can be a monolayer thick, hence the atomic layer. So the idea is that you are making a film by literally adding one atomic layer on top of another atomic layer. The great advantage of atomic layer deposition is that it leads to extremely smooth and conformal films. So if you look at the figure on the right, you can actually see what we have are very deep trenches that have been etched into silicon. How do we do these deep trench etching is something we will will understand when we do subtractive processing. It's done by deep reactive IR etching. You don't have to understand that for now. You just have to sort of notice two things. One, the aspect ratio of this hole is very deep. So it's very narrow, but it's very deep. So the aspect ratio is very high. And other thing you would notice is that the way the etching happens, it leaves a little bit of roughness on the surface. You can actually see there's a little bit of wriggle. On top of that wriggle, you see a certain white layer. That white layer is zinc oxide that has been deposited using ALD. Let me actually grab my pointer real quick. So that film is what is deposited by ALD, and how do we actually deposit these films that are extremely conformal? You see it follows the topology of the underlying silicon pretty exactly. The top roughness that you can see on the top is less than a nanometer, and it's conformal even very far deep below, right? So even the thickness that you see at the bottom, thickness that you see at the side, and the thickness that you see at the top are essentially the same. So ALD really shines in applications where you need a very conformal and a very smooth coating, all right? Typically the deposition temperatures are low, which is one more advantage, especially if your substrates are plastic or glass or something other than silicon wafer. If the film that you are doing growing is epitaxial, then this process is also called atomic layer epitaxy. In fact, the first when it was introduced, it was called atomic layer epitaxy, but later the atomic layer epitaxy did not become as popular as atomic layer deposition, because there was a bigger need of depositing amorphous or polycrystalline films, but of high quality. So that is where ALD is mostly used today for. You can use it for epitaxy, but that is rare. The mechanism we shall discuss later, but it basically revolves around two components. So in CVD, the way we would do a reaction is we would throw precursor A, precursor B, the two would react simultaneously and form the material that you want to deposit. In ALD, we don't flow the two together. We flow them one after the other. So they are not, let's say they are temporally separated, right? So when precursor A is flowing, precursor B is not flowing. When precursor B is flowing, the precursor A is not flowing. Either of A or B alone cannot make the material that you want to deposit, but A and B together can then make the material that you want. The trick to this process is that A and B are self-limiting reactions. So they occur at the surface, but then they don't continuously keep occurring. So once again, comparing to CVD, if I keep throwing a precursor for longer and longer, I would get thicker and thicker films. That is not what happens in ALD. Once you flow precursor A, you form a certain layer on top, but that layer is self-limiting. It doesn't grow in thickness the longer you flow the gas. Only when you send the precursor B does the chemical reaction complete and you form a monolayer of the material you want to deposit. So if this is not making sense, please wait a minute. We will spend a lot of time understanding this exact mechanism in the following slides. What sort of materials can we deposit using ALD? Well, the library is very, very large. You can deposit an oxides, which is the most popular use of ALD. Aluminum oxide, titanium dioxide, zinc oxide, hafnium oxide, silicon dioxide, etc. Increasingly, these processes are even becoming mass manufacturable. They are not just research and development anymore. People can also deposit metals. So you don't have to do oxides. You can deposit metals such as platinum, tungsten, copper. lately people have also started depositing nitrides. The nitride deposition is a little more complicated because nitrogen is not as reactive. If you remember the lecture on native oxide growth where we discussed growth of silicon nitride on silicon by flowing nitrogen, we realized that that cannot happen because nitrogen is a very stable and inert molecule and it requires very high temperatures to break nitrogen and form silicon nitrogen bond. So similarly, growing nitrides with nitrogen is not possible. However, just like in nitridation, we were able to introduce ammonia, and ammonia was a more reactive form of nitrogen, and we were able to react silicon with ammonia to form silicon nitride. We can do similar things here. So we can do ALD with ammonia gas, and that allows us to deposit nitrides. You can also deposit sulfides if you just substitute water with H2S. So a sulfur source, you can deposit sulfides. You can even deposit alloys, so which is that you can deposit oxysulfides or you can deposit oxynitrides. Right? You can even instead of component A and component B, which allows you to deposit binary materials, you can have a component A, B, and C, which allows you to deposit tertiary materials. Right? So those sort of details I will not get into, but we will get into the simple vanilla two component ALD, and the poster child or the base case study that we will continuously use again and again is aluminum oxide. Right? So this is what one cycle of ALD looks on a molecular level. So you start with a substrate and then you flow the component A. Now that component A is designed in a manner that it chemisorbs on top of the substrate to form a self-limiting monolayer. Okay. Once again, if you keep flowing component A again and again, it doesn't change the thickness of this chemisorbed layer, and that is simply because material A is not does not want to stick to itself. It's not condensing. It is simply chemisorbing on the substrate. So once the substrate is completely covered with a monolayer of component A, there is no space for further material to adsorb itself. Also notice I am using the word chemisorption, not adsorption. In its most strictest definition, ALD requires chemisorption, which means some amount of chemical reaction or chemical interaction is occurring between the substrate and the component. As we shall see later, this is what allows you to make the reaction irreversible. Okay, so just hold that thought. We'll come to it later. Once you are done with chemisorption of component A on the surface, then you flow the second component of your reaction. In this case, component B, and that component B is again designed in a manner that one end of the molecule can react with the component A. So it forms this bond, which is represented by these yellow figures. And what if you keep flowing B for some time, this reaction will go to completion and you will get a monolayer of component B that is covering the surface. Now what you have done in this process is you have started from a surface that had A functional sticking out and you have ended with a surface that has B functional sticking out. But more importantly, what you have done is you have formed a layer of reacted species that is both A plus B, and this yellow thing is typically the material you want to deposit. So if you want to, for example, deposit aluminum oxide, then this would be the aluminum monoxygen. Okay. The B is also a self-limiting chemisorption for the same reason that A proceeds to completion and does not get a second monolayer is the same reason why B would not get a second monolayer. After that, you purge all the excess B out of your system. And once you purge the B out of the system, then you introduce the component A. Now because there is no B in the gas phase, the A cannot react with anything in the gas phase, but A can react with the B that is sticking on the surface. So it does that reaction, again you form this yellow molecules of the material you want to deposit, and the A functional is sticking out. And if you wait for some time, then all these sites would react with component A, and you would end up with essentially a monolayer of yellow, which is functionalized by a monolayer of A. And if you think about it, now this is a deposited film, and this deposited film now has a monolayer coverage of A, which brings you back to where you started, right? So this is one complete cycle. So the next cycle, the whole process will happen all over again, and you would gain one more layer of the yellow stuff that you want to deposit. So in very simple terms, or in a molecular level, this is what ALD tries to accomplish. So now let's talk about the materials and precursors that are often used in ALD. So for cations, we typically use some metal organic. There's a very vast library of volatile chemicals that you can use. We have already discussed precursor selection a little bit in CVD. ALD arguably has a larger library. Typically, the precursors that are volatile tend to be from the general class of metal alkyls, for example, trimethyl aluminum or diethyl zinc. They sometimes are alkoxides, for example, this is titanium isopropoxide. Sometimes they are some version of amine, for example, this is a hafnium precursor that is an amine. We can be metal carbonyl, so this is a molybdenum precursor that is molyhexacarbonyl. So, these sort of precursors tend to be used. For the anion, again depends on what you want to do. So, for oxides the most common one is water. Water is both volatile at room temperature and is fairly reactive, but you can also use oxygen, ozone. Ozone does not store very well, so often it has to be made in situ using UV light. If you have access to plasma inside your ALD chamber, and we will touch upon plasma enhanced ALD later, you can even use less reactive forms of oxygen such as nitrous oxide or carbon dioxide. For nitrides, the most common one is ammonia. Then you can do sulfides, for which typically people use H2S, and you can also do phosphides. Lately people have started using gallium phosphide, indium phosphide, ALD, and they tend to use phosphine. Now, let us take the canonical example, and that is the growth of aluminum oxide using a trimethyl aluminum or TMA. In a lot of ways, this is one of the most ideal ALD reactions. More novel or exoteric forms of ALD sometimes deviate from the ideal. So, but before we start looking at the deviations, we should have an understanding of what basic, simple, ideal ALD looks like, and TMA is a very good example of that. So, the way the ALD of TMA works is you start with a substrate which you have ended with OH groups. So, you have a substrate on which you have OHs. Now, how do you get these OHs? Well, either you get this because the end of the last cycle gives you OH groups. If your substrate does not start with OHs, a common trick is to pulse a lot of water for some 10 minutes or so, and that pulsing of steam on top of the substrate will typically end up creating an OH group on the surface. But anyways, somehow you get these OH groups, then you flow in your precursor A, which is TMA. This aluminum, the metal alkyl bond is an extremely reactive bond. It reacts with these OHs groups because the aluminum's affinity to oxygen is very large. You form an AlO bond, and some of these organic groups continue to stick on the aluminum and stick out. So, and after that you flow some inert gas to purge all the excess TMA that has not reacted on the surface. So, after the purging step, this is what you are left with. So, you started with OHs group, and now you have these aluminum oxygen alkyl groups sticking out. Then you send your second reactant, which in this case tends to be water, and you can see the exact reaction, but basically the H will go to the CH3 group, the OH will go to the aluminum group. So, you will give out methane. Methane is volatile at room temperature, so it will just float away, and you end up with a structure that basically looks like a aluminum OH bond, right. Now, if there is this, if the substrate is high enough, then this aluminum OH bond can then dehydrate into aluminum oxide bond, and that leads to the formation of aluminum oxide. If you are not ending this chemical reaction here, then these OHs will then react with TMA again in the next cycle, and so on, and you will layer by layer keep growing aluminum oxide. The reason this is so popular and nice is once again, which is the USP for ALD, that you grow very conformal and very dense films. So, now let us look into a little more detail on this layer by layer business. So, just to again clarify the way we are doing the gas flow is we are turning on the TMA for some time. The time we turn the TMA on is called dose. So, you are looking at gas flow as a function of time. So, for this some amount of time you are flowing the TMA precursor, you are waiting for completion of a monolayer, right. So, that time is typically called TMA dose. This is often followed with a purge cycle. So, during the purge cycle, all the excess TMA that has not chemisorbed on the surface must be flushed out. So, typically you can do this with any inert gas. Nitrogen is the one most common. So, you flow nitrogen for some time to get rid of that excess TMA. Now, the chamber does not have any TMA save for the surfaces which have covered with a monolayer of TMA. Then you flow your component B, which is water. And again, the length of time you flow water is called the H2O dose or component B dose. You wait for some time for this reaction to complete, for a monolayer of OHs to form on the surface. And after this, once again, you flow an inert gas to get rid of all the excess water that is there in the chamber that has not reacted at the surface. So this is one complete cycle, right? Now, if you stick a quartz crystal in there and actually look at what is happening to the mass gain, it actually tells you a very interesting story. So you start from point 0, which is the TMA dose part. And during the TMA dose, what happens is because of chemisorption, you see an increase in the mass, which is expected. But this is a self-limiting reaction, remember, so it keeps going increasing, and at some point it flatlines. And the reason it flatlines is at that point there is no surface states for TMA to react with or chemisorb on. After this point, there is no point in waiting any further, so you turn off the TMA and then you do the purge cycle. During the purge cycle, nitrogen flows, all the excess TMA gets removed. But because this is a chemisorb process, you don't actually remove the TMA from the surface that is chemisorbed. So the chemisorbed is, think of it as an irreversible adsorption. So material can come in, do a reaction of some sort or do a chemical interaction, but does not have enough energy to get out in the time scales that we are dealing with here. So the TMA during this nitrogen flow, the TMA that is adsorbed on the surface does not go up, so the mass does not change, it remains flat. You give some time for the rest of the chamber to clean, and then you introduce water. When you introduce water, once again chemisorption happens, the mass increases, and once you feel that once you know that the reaction is completed and flatlining, you turn the water off and then do the nitrogen purge. Now there is this interestingly, unlike TMA, you do see some drop in mass here. It doesn't go all the way down to this portion, so some of the water remains, but with time the amount of water falls. Now this is often a non-ideality seen in a lot of precursors. TMA is an excellent precursor, it does not have this non-ideality, water does. And what is actually happening here is you think that the water is chemisorbed on the surface, but not all water, that's not the only mechanism at play. Some of the water could be adsorbed on the surface, and adsorption tends to be a reversible process. So the part of the water that is simply adsorbed may desorb while you are flowing the inert gas, right? So this is some amount of desorption occurring. Of course, if it completely desorbs, then that is no good because then you can't have a reaction. But that is not what happens. There is some reactivity between water and TMA, and because of the reactivity, a certain amount is chemisorbed on the surface, and that is irreversible. That water will not come out. So you see some amount of mass gain, and of course, this is the end of the first step of one cycle. Next, you will start again. Okay. So this is the amount of mass you gain per cycle or per step, right? Per cycle, you gain this much amount of mass, which is not exactly a monolayer per se. So atomic layer deposition is slightly has a slightly poor nomenclature. It seems to suggest that you always have one exact monolayer. That's a little misleading. The better way to think about it is that it has self-limiting chemisorbed layers. They sometimes are more than a monolayer, sometimes they are less than a monolayer. Often they are less than a monolayer. The exact details of course depend upon the temperature of the substrate, the precursor that you are doing, but overall the great news is that the process is very repeatable. So if when you are doing multiple cycles, each cycle does essentially the same thing. So overall the whole process is extremely repeatable and linear. I'll show you an example of what I mean by that. So this is something we have already seen, but this is just one step of one cycle, right? Now supposing you took some time and continuously keep doing these cycles one after the other. So what you would see is that your aluminum oxide thickness will start increasing, and it increases at a very predictable, very linear, very known value. So in this case 1.07 angstroms per cycle, right? Very accurate. And if you zoom in, you will actually see these small steps. Each of these steps represents one cycle where a little bit of aluminum oxide grew. And the thickness that you would see in each step is not exactly a monolayer, but it doesn't have to be as long as it's repeatable and consistent. Often what you gain in each cycle is called growth per cycle or GPC. This is a nomenclature we'll use in this lecture. And yeah, let's keep going. So let us talk a little bit more about this self-limiting nature of chemisorption. So for example, let's take diethyl zinc and water which react to give you zinc oxide. So if you look at the growth rate and you plot the growth rate per cycle as a function of dose time. So this is how long you leave the precursor A, in this case diethyl zinc, on, right. So how long you keep it on. So you are changing that time. So once again you start from 0. As the precursor starts chemisorbing on the surface, you will see larger and larger growth rate because you are absorbing more and more of the material on top, and at some point you get to the self limiting case where giving it more time would not add any more precursor. So till that point you are in the incomplete chemisorption phase. So you must give it this much amount of time, otherwise you have suboptimal growth. Once you have reached this point where you have as good a coverage as you are going to get, after that, if you continue to give longer time, then you don't add any more material, right. So it doesn't, the growth rate doesn't go up much. Also the material doesn't desorb, so it's a one directional reaction, so it just chemisorbs on the surface, you form this relatively complete monolayer, and after that it's very hard to change it. The little bit of change that you do see is some second order effect that is not terribly important. This is actual data, so the figure is a little off. Okay, so for details you can always look at this reference. Now the second thing to understand about chemisorption is its dependence on partial pressure. So if you remember the CVD lecture, we continuously talked about how partial pressure is one of the key parameters to control the growth rate in CVD. No matter what regime you are in, no matter what type of reactor you have, partial pressure will always change the growth rate inside. ALD is very different because the reaction is irreversible. So there is no equilibrium, there is no incoming and outgoing. The outgoing is 0, so it's only incoming, and because there is only incoming, the growth rate tends to be fairly independent of the vapor pressure. So here example again of TMA in water, which you use to form aluminum oxide. So if you were to change, if you were to say keep the vapor pressure of TMA constant at 0.1 millitorr, but then keep the vapor pressure of water constant at 0.1 millitorr, but change the vapor pressure of TMA, right. So no matter what vapor pressure of TMA you maintain, the growth rate will be exactly the same. You can do the ulta, on the reverse, where you maintain a 0.1 millitorr of TMA, but then you change the partial pressure for water, and once again you don't see any change. So very much unlike CVD, and this is an important point, the partial pressure of precursors sort of doesn't matter, only its temperature does. And that actually simplifies things considerably, because in CVD we went through so much pain to maintain nearly uniform flow, roughly the same partial pressure. There's very complicated shower heads, there are very complicated pressure control systems. ALD tends to be a lot simpler because pressure control is not that big a deal. So now supposing I give you a new precursor A and a precursor B and ask you to come up with a recipe for ALD, how do you go about making a new recipe? So all you have to do is sort of understand the basics of how ALD works, and then just optimize the 4 parameters that you have under your control. What are the 4 parameters? You have the dose of component A, you have the purge of component A, you have the dose of component B, and you have the purge of component B. So what you would do is you would do the deposition, you would plot the deposition per cycle or growth per cycle of that precursor and change the dose. So you will change the dose from some small time to some large time, and you would plot the GPC. So for very short times you will have incomplete chemisorption. Because of incomplete chemisorption you will have suboptimal growth rates. But once you reach the case where there is enough time for the component A to form a self-limiting layer on top of the substrate, after that increasing the dose time further, which is this blue TMA dose, further does not do anything. The growth sort of saturates. So what should be the ideal optimal length of your dose cycle? The optimal length of your dose cycle should be exactly this time. Any less and you have suboptimal ALD, any more and you are just wasting time. Similarly for the purge cycle, you would plot the deposition per cycle for various purge times. For very small times you will have TMA, excess TMA that just hangs out in the chamber. Now this is TMA that is not absorbed on the surface but is just inside the chamber. This is bad because this TMA will then react with the water that you will put in the subsequent cycles and do a sort of CVD type reaction, not an ALD type of reaction. You always want ALD to happen on the substrate, not in the gas phase. So, if you were to leave some excess TMA, then that would artificially enhance your growth rate, but that growth rate is not a proper ALD. So, you want to avoid that. So, what you will see a slightly enhanced growth initially, but as you increase the purge times, the growth will fall, but at some point reach a point where there is no more excess TMA in the atmosphere of the chamber or in the ambient of the chamber. All the TMA is only present on the substrate, and the TMA on the substrate is irreversible, it is not going to come out. So, now your deposition cycle will once again saturate. What should be the length of your purge cycle? It should be as long as exactly this point. Any less and you have excess TMA in the chamber, that is messing up your ALD, any more and you are wasting time. Once you are done this with component A, you can do the same optimization with component B. We will once again plot the growth per cycle or deposition per cycle as a function of various H2O dose timings and H2O purge timings. And the goal is to always reach this point where the growth is self-limiting, where the growth saturates. You always want your ALD to be in the saturated regime. Once you have done this, then you will have your 4 parameters, and that would be your optimized recipe. So, what is happening here? Too little TMA. What is happening here? Too much TMA. You don't want to be here. What is happening here? Too little water. What is happening here? Too much water. You don't want to be in these cases. You always want to be in the case where the growth saturates. Okay. Now, what happens if you are in these red regions? Well, if you are in the red regions, you will often get non-uniformity, and let's talk about that a minute. So, unlike CVD, ALD chambers are often not designed keeping gas flow in mind. And the reason they are not designed with gas flow in mind is because the reaction is not happening continuously, it is happening in these steps. And in each step, you sort of let the equilibrium happen, right? Your assumption is that every step will be self-limiting, every step you will wait until a monolayer forms in a conformal and uniform fashion. So, you don't really need to worry about gas flow dynamics. Now, if in that chamber, you have a system where there is CVD like growth happening because of either excess H2O or not enough H2O, then that leads to non-uniformities. So, here is an example. So, if I am not, so supposing you had a deposition per cycle and this is component A and the component A dose cycle. So, once again suboptimal dose because not enough material is going on, at some point it will saturate. So, this is the optimal dose. Now, if you were to look at a wafer that was processed at a suboptimal dose, which is the red square, and the one that is processed at an optimal dose, which is the blue square. In the red square, you will often see a non-uniform deposition. So, if you keep a wafer such that the inlet is on the left, the pump is on the right, then this portion tends to start showing lesser deposition than the front of the wafer. While if you do this in the optimal case, then there is no non-uniformity, you would get a conformal, smooth, ALD-like film that you expect, right? And with that, which brings us to something that we started with, which is what is the USP for ALD? Well, the USP for ALD is uniformity and conformality. So, if you just look at this slide once, this is something we even saw earlier, but now you can probably appreciate it more, that if you have these very deep channels, right, and you want to coat a very thin layer of conformal aluminum oxide or some other material, that is same thickness on the side, same thickness on the top, same thickness on the bottom, ALD is extremely good. Because ALD does not depend upon the flow dynamics of the gas, it does not depend upon the gas flow patterns, it does not depend upon diffusion. By and large, it is a chemisorption process. All that will happen in a higher aspect ratio structure is that your dose times will increase or that your purge times will increase, but you would still get the uniform film. So, here is an example, again a very deep trench, or what we are looking at a cross section at point A, a point B and a point C, and everywhere we essentially see the same thickness of ALD deposited material, which is what we want. So, with that we will actually end this lecture. In the next lecture we will look at some more complicated things about ALD, for example the deposition windows, plasma enhanced ALD, some aspects of nucleation, etc. Thank you.